I would start with this quote from John McCarthy, and John McCarthy is considered to be like the father of artificial intelligence. So in 1961, I don't want to read the definition, but the thought by that time is actually how to make the computer, the one that was originally invented maybe in the 40s, how can make it as a public utility. Like if you have a possibility, they have this kind of computational power present in a computer, can be treated as a public utility the way we take service from telephone systems, then this will be like a basis of a new and important industry. So since that time, the innovation and research was all going into the direction that how to make this kind of computers are shared among users. And when I say shared among time users, they will think about being time shared, like users can time share the PC. And that concept that was there in the 60s, once we reach the containers and we see how they share the CPU, you'll see that the two ideas are very similar, not similar, but they correspond to each other. So since the 60s, researchers and scientists, they were working on the idea of time sharing a certain PC. And that was a project back that I'm bringing in 1963. That was the idea on how to share a single computer. But guess what? Sharing a single computer can be a significant task, but actually having connectivity to that computer from different endpoints, this is actually an important milestone, because if you are able to give users the connectivity to that PC and you're able to give them the idea of time sharing, then most probably you'll be able to demonstrate your experiment that you are able to give multiple users shares of that CPU. And that's why in 1969, this important initiative, the ARPANET, that was the basis of the internet. That was actually the first packet switched over TCP, TCP over IP network that was introduced. That actually made the concept more so that now you can connect multiple endpoints over IP to a certain point. On that certain point, you are trying to do CPU sharing. Then the idea now makes sense that users can share a computer resources. During 17th and 19th, there was the evolution of the concept of virtual machines. The ARPANET, which is actually the internet, I mean the base of the internet, they adopted the TCP IP. And actually in 1991, when the internet was publicly adopted, the World Wide Web, that was the kickoff actually for knowing that there is a sort of a cloud solution that can be accessed from anywhere. So two concepts that actually gave a boost to the cloud evolution: the idea of computer sharing or resources or CPU sharing, and it was all about time sharing by that time, plus the connectivity, and that's represented on the internet. Starting from the 19th, and actually I will even reflect to what was there in the group 5 slides. Starting in 19th, that was the evolution of the virtualization and the concept of software as a service, that someone can provide a service over the cloud. For instance, Salesforce software as a service. As you see, AWS was 2002, iCloud 2011. So this was the evolution of having a service that you can consume across over internet. But what is significant for us, and that was also in group 5 slides, that the concept of virtualization, and by that time it was the rise was very closely coupled with the hardware architecture, which I'm going to explain today. So guys, can you just mute yourself just to make sure that I don't have an echo? So in 2001, started in 1999. Sorry guys, can you hear me now, or you cannot hear me?
Yes,
We can hear you.
Okay, because I got a message that I'm not. Some people cannot hear me. Okay, let me just do again. So back to the 1999-2001, That was the VMware contribution, well-known contribution in the industry when they succeeded to do the first x86, which would be Intel by that time architecture, or that I'm going to talk about today. They were able to do this kind of virtualization. Like for instance, you get some sort of resources, you do partitioning of these resources, and you start to give these resources into different applications, which under the name of virtualization. Also in 2007, the concept of, I would say there was some other concept called hypervisor, which we are going to explain. Open source KVM, which is the well-known open source hypervisor, was issued in 2007. All these, I would say, historical landmarks or incidents, most of them were embraced by the enterprises or the IT. What is significant for the telco is 2012. And that was the start, I would say, of the cloud journey at telcos, when a white paper was published in October 2012 from the major operators, telco operators in the market. That white paper just said that we have a lot of pain points. Let's try to embrace this virtualization technique, cloud techniques, and bring them to our industry. So if you ask anyone who's working on the virtualization on telco domain, when was the trigger or the starting point? It was 2012. And by that time, because we love standardization, they chose ETSI, European Telecommunication Standardization Institute, to be the home of NFV, which is Network Functions Virtualization Standardization. From 2012 to 2015, there was no telco big adoption. VMware was really leading by that time because OpenStack solutions was not that mature. But most of the telco deployments were based on HCNFV. In 2015, there was some sort of a boom of a telco cloud deployments based on that HCNFV architecture, whatever, and most of deployments were based on OpenStack and VMware. And what we are in now, and that again maps to what the Rama is presenting, starting from 2020 plus, with the rise of 5G, we saw the rise of something called cloud native adoption, which is more and more BNFs or network functions are starting to be based on containers and with other aspects of being cloud native. So this is the journey. The significant part here is that we are going to touch most of these buzzwords in our program. Okay, so don't worry about the buzzwords. We are going to touch that. But the main thing here is that starting from 2012, we started in telco domain to embrace, to host or to welcome this kind of cloud techniques and the virtualization technique that have started even from the 70s. Let me just admit Ahmad Mukhtar and Muhammad Hamada. Okay, Ahmad and Muhammad, you're back. So jumping to our topic, we have 30 minutes. So I'm going to show you now a diagram. It's a very informative, okay? It's cloud stack, and it is called infrastructure as a service, okay? Don't worry about these functional blocks. We will talk about it big time, but I want you to focus on something called cloud infrastructure, okay? And cloud infrastructure, by definition, there are three main bricks. So cloud provides compute, CPU, core power, execution environment. Cloud infrastructure provides storage for the applications and provide networking. So usually in telco, when you talk about cloud infrastructure, we are talking about the solutions from hardware perspective and sometimes software that actually fulfills the compute, storage, and networking. So for instance, if you get a service from Amazon, AWS, just having an infrastructure as a service, which is basically a virtual machine, regardless what is virtual machine, we'll talk about that. Most probably you'll be able to take a virtual CPU, computational power. You will take some storage solution for your application, and you'll get some sort of connectivity that will allow your application to run and to have this kind of continuous service. So now we are going to focus on that part, which is the compute. What is the cloud compute? And it is a bottom-top approach, because as I said in the beginning, one of the problems that I met when I first tried to learn these cloud techniques, is that I looked from top to bottom. So I was the application owner. And then I found there are a lot of logic related to CPU, virtual CPU, threads, hyper threading. So we were totally lost. But it is very essential, very important to all of us as telco senior profiles, or even as usual as professionals, to understand how the actual server works, how this cloud gives you computational power. So let's focus now on the compute. And let me take you to this slide. So in this slide, I'm telling you that most of the servers that you see now in the telco domains away from the edge, I mean, you see it in the data centers, in the core side, are based in x86 architecture. And that x86 architecture, that's the architecture developed by, that's actually the architecture adopted by Intel and AMD and the key players, I mean, in the market. And usually, most of the servers that we have been using for the last 8 years, they are based on Intel. I mean, people working on cloud, they know that. And you always see this kind of Xeon processor are the one used for servers. So usually, if you review a BOQ, you review a cloud that you are building on your private cloud or anything in your enterprise, most probably you'll find servers with this kind of processors. So for us, if we don't understand these buzzwords, it will be a black box. Okay. For instance, I'm telling you here that's an example of a BOQ, that you have a specific server, which is 2-time Intel Xeon Gold 6240, 2.6 gigahertz, 18 cores, 36 threads. So you need to understand what does this mean and how does this eventually contribute to your application. And that's the starting point of my 30 minutes today. So let's focus on that. Let's understand what is a CPU, what is a thread, what is core thing, and then we will build on top of that for the next session. Any initial comments or questions before I start? Okay. So Muhammad Shabu, you are admitted. Sorry, I didn't see that. So let's now take a look on how does it look from bottom top, how actually what constructs a server, what gives the computational power, because at the end, the cloud is based on servers, and servers provide this kind of computational power. So you have to understand that kind of topic. So when you work with in telco cloud, in cloud deployments, you always see the term CPU and socket. So I'm here just to explain the differences. So CPU, that's the main brain, right? CPU, this is actually the one that executes the instruction, the one that fulfills the logic. So CPU is the brain of the server. And you have a lot of means to increase the efficiency of a CPU, of a central processing unit, by adding more cores, by increasing the frequency, the clock. But still, CPU is actually, when someone says the CPU, that's the brain of the server. That's actually the one that fulfills the instructions. That's one that does the logical operations. That's actually the one that controls the other hardware components, like, for example, interface cards, storage arrays, memories, caches. So that's the main guy. And as you see, the main processes for that CPU is 4 things. And I will focus on 2 things, fetch and store. And the word fetch, like to get the instructions from a memory, and store the output in the memory. And that shows the close relation between a CPU and memory. And that's why, again, whenever in telco, we say compute in the telco terminology means CPU and memory, because they are very closely coupled. Okay, so when someone says compute in telco, that's the CPU and a memory. Okay, so you fetch the instructions from the memory, you interpret these instructions, and then CPU does some sort of decoding, because this kind of the instructions is written in assembly instructions, so he has to convert that into a binary format for execution, and then the execution part, and then the output or the execution, this instruction is stored again in the memory. So that's why CPU and memory is very coupled, and I have one slide to show that. Okay. How we can improve the performance of a CPU? You can increase the clock speed, and clock speed, actually, that's the frequency which a CPU executes the instructions, or you can increase something called number of core. I think you all heard about quad core, right? Like the CPU with 4 cores. So there's a practice, and I will show you to that in one CPU, you can have multiple cores, and I'll explain what is core and what is CPU. So that's the CPU. Let me just admit Tamer Fauzi, and we go back. So that was a CPU. To have that CPU placed on a motherboard, which is the server motherboard, you need the socket. And that's a socket, that's actually some sort of a layer, physical and electrical layer, where you put the CPU, and that connects the CPU to the motherboard. Okay. So for example, if you have 2 CPUs, then you have 2 sockets. But here we want to talk about the terms being used in the telecom environment, in the telco cloud environment. When someone say socket, okay, he implicitly refers to the motherboard. For example, when he says that this server has 2 sockets, then this server has 2 boards, or this server has 2 main CPUs. So we usually use the socket to actually give a characteristic for the server. When we say server with 2 sockets, then server with two boards. Server with 4 sockets, then server with 4 boards. In telco, most of our servers being used in telco cloud are 2 sockets. And that will appear in the next slide. So CPU placed on a socket, and then that socket connects the CPU to the motherboard. The motherboard, and we don't usually say motherboard in the servers, I mean in telco terminology. You can call it anything, central port, central circuit. That's have the slots that has the CPU, that have the memory slots, that have the storage interface, the storage SSDs or disks, that have, for example, network interface, what we call it NIC, network interface card, that has the power connector, which is classically a motherboard, like the one that you see in your PC or whatever. So these are the 3 levels. These are the 3 levels: CPU, socket, and board. Okay. When you start to work with the telco cloud, you get other terms being used. One of them is NUMA. I'm not sure if you heard about that or not. NUMA is actually non-uniform memory access. Non-uniform memory access. It's a kind of architecture, okay, that allows the CPU, if you, for example, see CPU 0 in socket 0, classically, it should interact with the memory in the same socket, in the same motherboard, to avoid inter-processors or inter-sockets communication. But NUMA, the architecture itself, it says that CPU 0 can still use the memory 0 in the same socket, but still can use NUMA 1, using the bus between the 2 sockets or 2 processors. Okay, that's the architecture, or that's the concept, that non-uniform memory access, that CPU can access the memory in the same socket, or sorry, same processor, and also can access memory in other processors. And you see in telco cloud, somehow it is always recommended, and we try to do our best to make sure that CPU 0 or cores in CPU 0 are using the memory on the same socket. Okay, the word NUMA is being used to describe the socket. For instance, when I say NUMA 0, that implicitly means first socket. When I say NUMA 1, that's implicitly socket 2. And that's the term being used in the telcos. For example, when you go to do some Linux command, and you display this kind of things, you find NUMA 0 and NUMA 1. So that's why, for example, when you talk with someone working on the cloud, and telco cloud, when you talk about the socket 1, you always refer it to NUMA 0. when you want to tell that guy that I need my application to run in the first socket, you tell him I need my application to be in NUMA 0. Okay, so that's the term NUMA. Okay, non-uniform memory access, and you can see it clearly here. Okay, but NUMA 0 includes the CPU 0 and the corresponding memory, corresponding input and output devices. That's actually the first socket. Okay. So
one question, one question, Karim, please. You mean that the NUMA enables the CPU to access the other memory? For example, if you back to the last slide.
yes, it is an architecture that gives this kind of flexibility that the CPU 0 can access memory in first socket and also can access memory in the second socket.
But normally we are not using this flexibility. We are trying to make it the same socket, right?
Good question. If you don't control it, if you don't put guidelines by configuration, by whatever policies, then the CPU 0 can do that.
Okay.
And you will see in the next, like, let's say in maybe 5-6 sessions, that what are the tools that we do to control this kind of pinning, that whenever application using CPU 0, it gets the things fetched from memory in socket in the first socket, not the second one. Okay?
Great. Great.
And a very important concept, as I said, as an evolution to increase the CPU efficiency, we introduced or Intel introduced or whatever, or the technology introduced the concept of having a multi-core. So one CPU can have multiple cores. One CPU can have multiple cores. And this is very, I would say classically, you find your laptop, your PC is one CPU with like 8 cores or even the mobiles. In the servers, it's very common to find one server having 2 sockets. Each socket or each CPU have, for example, 24 cores. So the idea of having more cores reflects directly to the efficiency of the CPU. Whenever you have more cores, classically, you are giving more execution environment, so you are increasing the performance of the CPU. Okay? So I want you to introduce the concept of multi-core processors that you find always in our servers, in telco servers, in IT servers, in whatever servers, that each CPU have number of cores or 8, 12, 14. Okay? Make sense?
Yes.
Okay.
That's
So now,
great.
so now we have NUMA 0 or socket 1, whatever term you want to use. It has a central processing unit, and that CPU is having multiple cores. Here in the drawing, it's 8 core, and that kind of 8 cores have access to the local memory and local input and output devices. And this kind of quick path interconnect the path between the 2 boards, facilitate the communication inter NUMA communication. Okay.
Great.
Now, most probably, if you are working with applications or with VNFs, no one is telling you I need 16 core for my VM. Usually, he tells you I need 16 CPU for my core for my VM. And by the way, guys, till now I didn't talk about any kind of virtualization. This is just a pure hardware stuff. Okay. The thing here that these cores, whenever you boot the server, okay, these cores are being presented to the operating system as CPU. So operating system, okay, sees each core independently, sees each core as a standalone CPU. And that's why the term CPU comes now into the picture. Because I was telling you before, I bet you never heard like a certain application like core function, DGS, NP gateway require 15 core, or sorry, 16 core. They require 16 CPU. Why the term CPU now comes again? Because whenever you boot up the server, the operating system recognizes these cores as standalone CPUs. And they usually get this kind of sequence. Like in NUMA 0, you get 0, 2, 4, 6, 8, 10, 12, 14, whatever. And you get the odd numbers of CPUs in the NUMA 1, 3, 5, 7, 9, 11, 13, 15. So here is another important concept, which is the logical processor. That whenever you put server, you get the logical processor like CPUs mapping to the physical cores. Philo, yes?
I have a small question here. Are we talking about virtual CPUs or
No,
actual CPU?
No. We haven't brought anything related to virtualization. That's a pure physical stuff.
Okay. So the cores, the 16 cores of the actual CPU, it's seen as 16 individual CPUs.
So the
right?
cores now are CPUs. Now the operating system of a normal server sees this 16 core as 16 CPU.
All right. Thank you.
And
Okay.
Karim, when CPU is rebooted, it reboots the all the groups, yani 0, 2, 4, 6, the groups hosted on one specific CPU.
Actually, yes. When you boot the server, you boot everything. You put the two NUMAs with the codes.
Thank you.
Okay. So the operating system, something like Linux, for instance. So Linux sees these codes as CPUs. Yeah, anyway, when you do a Linux command, you find that CPU 0, CPU 2, CPU 4. Let's forget about this code. Now we are talking about logical processor. Okay?
Okay.
And remember, this is not related at all to virtualization. I just want you to understand how the servers work. Okay? I will add another detail, which is very essential to the telco cloud and people working on this thing, the concept of hyper-threading. The concept of hyper-threading. If you enable this feature, and that's a BIOS feature, not related to virtualization, okay, founded by Intel, each CPU, okay, natively, if you enable the feature, will appear as if they are two CPUs for the operating system. How is that being done? It's using the concept of threads. Okay, so what is thread? Thread, you can think of it as follows. You all can see me, right? You can see me, right?
Yes.
So my CPU is my mouse. I eat stuff, and thread is my arm. So I bring things from memory. I do the decoding, the execution, and then I put it in the memory bank. So that's a thread. Okay, that's a thread. But there are some times when the CPU is idle, thread is not fetching any information. So I can use this slot to have another thread bringing data. Okay, so by definition, the thread, it's a unit of execution, or it's a set of instructions that's being fetched. That's a thread. And they all map to a single CPU. So now I have two threads. So now the operating system, they think, or it thinks that I am two CPUs. That's why if you enable the hyper-threading feature on the server, the operating system will always see the CPU as two. For instance, CPU 0, CPU 16, CPU 2, CPU 18. These are the threads. Okay? Are you still following, or did I confuse you?
So in this case,
Yeah, I'm following, but can you repeat it again, Karim? I'm sorry.
Okay. So the CPU here, that's a processing unit, right? That's a processing unit that fetch the instructions from the memory, that does the decoding, that does the execution, and then store the output in a memory. That's the classic CPU 024. Okay? We are okay, right?
Yeah, okay, yeah, okay.
With hyper-threading, the feature from Intel, okay, Instead of having one thread of the CPU that brings data and then takes data from CPU to the memory, this kind of thread, okay? It introduced the concept of hyper-threading. Like each CPU will have two threads. The thread is actually the unit of the work that can be executed. So now you have two. Still one CPU, physically one doing execution, but now you have two arms to feed the mouse. And that's why the operating system sees that CPU as two CPUs because it sees two arms.
Okay.
And from that point, the term thread will be always used. That, for instance, forget about virtualization. With that setup, if a certain application is placed on that server and it requires 6 CPUs, okay, 6 CPUs, then most probably it will capitalize on the 6 threads, the first 6 threads, 016, 218, 420. So thread is now a CPU, and there is no virtualization yet. I'm talking about just pure hardware stuff. Okay?
Karim, but yeah, this means that in this examples we have 2 threads, right?
Exactly.
But if we have, for example, a bigger number, like 36 threads or something, this means that every CPU are 36 small processing unit, right?
It's a good point. You can have multiple threads per CPU, and for sure there is a scalability figure. But in telco, the common configuration is having 2 threads per core chip, the classic hyper-threading of Intel. And sometimes they even disable it. Okay?
Okay, great.
Clear? So now.
Clear, yes, great.
So now, when we take a look on any BOQ that you may have in your work, or even that slide, when we start to read now that BOQ bill of quantity item, we can now start to understand, to relate. So it's saying that processor 2 time Intel, whatever. So 2, that's the sockets. It tells you that it has 2 boards, 2 sockets, 2 NUMAs, okay? And then Intel Xeon Gold, that's the Intel Xeon Gold 6240, that's the model name of the board, of the server. 2.6 gigahertz, that's what we call the clock speed, okay? That's the number of cycles the CPU can execute per second. And classically, we know, even since we were young, when you go with the high clock, you get better performance, right? Because that's a classic thing. But nowadays, the focus is not to increase the performance by increasing the clock, by increasing the cores, number of cores. That's the common way of increasing a server performance, is to have more cores. And it is telling you that I have 18 core in each socket and 36 threads. I'm not the one who did these celebrations. Okay, but now the line is clear that each socket have 18 core with hyper-threading enabled. It is 36 threads. So here you have 72 threads. You have 72 CPUs, physical CPUs or physical threads can be allocated to applications. Clear?
Yes.
And every small thread have a speed of 2.6 gigahertz, right?
The all threads are enjoying or are sharing the same clock speed.
Okay.
But from now on, from people working on cloud, coming from telco background, we will not talk a lot about clock. Most of our talks will be about the cores, the threads, the virtualization, how we are going to take these threads. But till now, there's no virtualization. This is the computational power of the server.
Okay, so this means that we have 2 NOMA, right? Every NOMA have 18 core, and every core have 2 threads.
Yes.
So total is 70.
But NOMA is a technical term. If you are in the BOQ phase, you are like an account manager, something like that, then you have 2 sockets. That's the term used. Okay.
Excuse me, 72 what?
72 thread or 72 CPU, because at the end, the operating system will see each thread as a CPU. Okay, so if now we count, we have 2 sockets. Each socket is 18 core, which is 36 threads. 36 threads times 2, 72.
72. Yeah.
So 72 CPU. The operating system will see that server as 72 CPU to be allocated by, or to be processing whatever applications you start to onboard. And that's the virtualization part. We are going to discuss it in next session. But now I just want to build the foundation on how to interpret the hardware part.
Karim, I'm sorry, I have one question. 36 threads here, we already multiply by 2. My understanding is we have 18 logical cores, right? And each logical core can handle up to 2 threads.
No, it's 18 physical code. That's
Physical. Okay.
yeah.
Okay, got it. Thank you.
Physical code. He's telling you that I was able in each NUMA to increase the CPU efficiency by adding 18 core physical core to each CPU.
Okay, so this is a physical course, and by enabling the hyper threading, we'll go to 72, right?
Yes, and why don't I say 72 cores? Because I know that operating system, once the server is booted, it will see that these cores as CPU.
Yeah, got your point. This is from the application level point of view.
No, from operating system. We call it the host operating system, like Linux. It's not the application.
Okay, thank you.
Okay?
And the 18 core is hosted on the 2 socket, not one.
No, it's one socket. 18.
Okay,
18.
that's not like the example we had before. Before we had 8 plus 8, now it's 18 plus 18.
18, yes, and the most common, I think, is 24. Yeah, this is a server configuration that I see always in Telco, 24 core per socket. When we go to virtualization, it'll be even more interesting. You will see how these codes are corresponding, or how they are assigned to the different application, different virtualized application. That's a very interesting stuff. But if you don't know that basis, you will get confused. I hope you're not confused already, but it's you will see it in the virtualization.